Today we will be doing hydrogen. See, the configuration of hydrogen is 1s1, which means that like all alkali metals, it has one electron in the s orbital, and therefore like alkali metals it is expected to show properties which are similar to alkali metals. For example, if it loses this electron, then it becomes H plus, and just like alkali metals. Also, like alkali metals, hydrogen forms like alkali metals, hydrogen forms oxides, halides and sulfides. So these are the properties of hydrogen which are similar to alkali metals. Its configuration is similar, NS1. It is capable of losing the electron and becoming H plus, and like alkali metals it forms oxides, halides and sulfides. However, its ionization energy is high. The ionization energy of hydrogen is high, and in fact the high ionization energy makes it resemble halogens. Another thing is, like halogens, it forms a diatomic molecule. You are aware that hydrogen is present as H2. So like halogens, it can combine with elements to form hydrides and a large number of covalent compounds. So like halogens, hydrogen can combine with other elements to form hydrides and large number of covalent compounds. So you can see one thing, that hydrogen has properties similar to alkali metals and also properties similar to halogens. So as a result, hydrogen is given a unique place in the periodic table. It is placed neither with the alkali metals nor with the halogens. Now we come to isotopes. Hydrogen has three isotopes. They are called protium, deuterium and tritium. So hydrogen has three isotopes: protium, deuterium and tritium. Now you know that all three have the same atomic number but different mass number. So their chemical properties are almost the same, but their physical properties have considerable difference due to the difference in mass. So these are the three isotopes of hydrogen. Now let's discuss the preparation of hydrogen. So preparation of hydrogen can be done by the reaction of granulated zinc with dilute HCl. If you react granulated zinc with dilute HCl, that is one way of preparing hydrogen. The other way is reaction of zinc with aqueous alkali. So zinc with aqueous alkali can also give the formation of hydrogen. So these methods of preparation of hydrogen are laboratory methods. Now what about the commercial methods? Commercial method, one very well-known commercial method is electrolysis of water. Now you know that water itself is not a very strong electrolyte. So to make it a good electrolyte, you need to add traces of an acid or a base. After that, the electrolysis of water will give hydrogen and oxygen. Now, if you perform electrolysis of aqueous barium hydroxide and using nickel electrodes, if you perform electrolysis of aqueous barium hydroxide using nickel electrode, in that case you will get hydrogen which is 99.95% pure. So electrolysis of barium hydroxide with nickel electrode is one very good method of getting hydrogen of high purity. Now, if you perform electrolysis of brine, then during the electrolysis of brine, these are the reactions at cathode and anode. At anode you will get chlorine gas and at cathode you will get hydrogen. So the overall electrolysis reaction will be this. This is the overall electrolysis reaction. Na plus Cl and you get chlorine at the anode, hydrogen at the cathode. So this is the overall reaction for electrolysis of brine. So this is also a very important commercial method for manufacture of hydrogen. Now, if you take any hydrocarbon and react it with steam at a high temperature in presence of catalyst, this is the reaction. So a very specific case of this reaction will be CH4 plus H2O is equal to CO plus 3H2. Now this reaction is applicable for steam with hydrocarbon. It is also applicable for steam with coke. At the end of the reaction, we get a mixture. This mixture is known as water gas. Now, this mixture itself is used to synthesize methanol and also hydrocarbons. So this mixture is used to synthesize methanol and also a large number of hydrocarbons. That is why it is also called synthesis or syngas. So this mixture, which is called water gas, is also known as syngas. Now, it is possible to produce syngas from coal. So if syngas is produced from coal, then the reaction is called coal gasification. So in this coal gasification reaction, what we can do is that the carbon monoxide which is produced can further be treated with steam in presence of iron chromate catalyst to increase the amount of hydrogen. So we have got hydrogen from the reaction of steam with coal, but now we are using the carbon monoxide which is produced to further react with steam in presence of iron chromate catalyst to give carbon dioxide and hydrogen. So this can be used to increase the amount of hydrogen. This particular reaction is also known as water gas shift reaction. Now we come to properties. Now in physical properties, you can say that hydrogen is colorless, odorless, tasteless, combustible, lighter than air, and insoluble in water. So it is colorless, odorless, tasteless, combustible, lighter than air, insoluble in water. Now let's come to the chemical properties. See, hydrogen is a diatomic molecule, and the bond enthalpy, the HH bond enthalpy, is the highest for any element. So if you want to obtain atomic hydrogen, then you require a very high temperature. Such high temperature can be provided by an electric arc, or it can be provided by UV light. So in an electric arc or under UV light, you can get atomic hydrogen. Now, what are the reactions of hydrogen? First of all, it reacts with halogens to form halides. Now, the halogen in this reaction can be fluorine, chlorine, bromine, or iodine. Now, if it is fluorine, the reaction can take place even in the dark, and if it is with iodine, it requires a catalyst. So this is the first important reaction with halogens. Secondly, reaction with oxygen. You can either use a catalyst or you can apply heat. And as a result, the reaction is highly exothermic with the production of H2O. Reaction with nitrogen gives ammonia. So H2 plus N2 gives ammonia. This is also a highly exothermic reaction, and in fact this method is the method for manufacture of ammonia by Haber's process. It reacts with metals to form hydrides. Any metal can react like this to form hydrides. Apart from reaction with metals, it can also react with metal ions. And metal oxides. So with metal ions, this is the reaction. So the metal ion has to be present in an aqueous solution, and it will get reduced by the hydrogen. And this metal oxide, it should be of metal less active than iron. So these are the reactions of hydrogen with metals, metal ions, and metallic oxides. Now, reactions with organic compounds. Now you will see that with organic compounds, some famous reactions, this is actually called hydroformylation. So in hydroformylation of alkenes, H2 plus CO gives aldehyde, and that aldehyde may further reduce to give alcohol. Apart from hydroformylation, another very well-known reaction of hydrogen in organic chemistry is reduction of alkenes to alkanes. You know that reduction has got practical uses. It is used to convert vegetable oils into fats. For example, oils into vanaspati ghee. Now we come to the uses of hydrogen. First, very important use of hydrogen. Hydrogen is used to manufacture ammonia. And by the way, ammonia in turn is used to manufacture HNO3, and also it is used to manufacture fertilizers. So hydrogen is primarily used to manufacture ammonia, which in turn is used to manufacture HNO3 and fertilizers. So second one is that you can start with vegetable oils, which I was telling you, and you can convert them into vanaspati ghee. Third one, it is used to manufacture methanol. This is the reaction for that, carbon monoxide plus hydrogen. This is cobalt catalyst. So these are some of the very important uses of hydrogen. Then it is used to prepare atomic hydrogen torch and also oxyhydrogen torch. Now these torches, atomic hydrogen torch and oxyhydrogen torch, they are used to generate very, very high temperatures of around 4000 Kelvin. So they can be used for cutting and welding purposes. For example, in atomic hydrogen torch, what happens is that atomic hydrogen atoms are allowed to combine on the surface which has to be welded, and that combination is able to generate so much temperature. Another thing is that hydrogen is used as a rocket fuel. So this is a very important use. And hydrogen is used in fuel cells. So fuel cells are used for generating electrical energy. So compared to many other fuels, it is absolutely non-polluting. That is the advantage. So these are the important uses of hydrogen. Now we come to hydrides. Now hydrides are of three types. First is ionic, which are also known as saline hydrides. Now what happens is that the ionic hydrides are usually formed with alkali metals. For example, let us say sodium hydride is an ionic hydride. Now, if you look at hydrides like LiH, BeH2 and MgH2, then they also have a significant covalent character. So even though they are expected to be ionic hydrides, they have a significant covalent character. Now all the ionic hydrides are crystalline, non-volatile, and non-conducting. However, if you consider them in molten form, if you consider the hydrides in molten form, then in molten form at the anode, they can liberate hydrogen like this. Now the thing is that ionic hydrides react violently with water, so the reaction is very violent to produce hydrogen gas. Now compared to other ionic hydrides, lithium hydride's reactivity is much less. So lithium hydride is essentially used to prepare other hydrides. So lithium hydride can be used to prepare other hydrides like this. So lithium hydride can be used to prepare lithium aluminum hydride, it can be used to prepare lithium borohydride, and so on. So these are the details of ionic hydrides. Next we come to covalent hydrides. Now, covalent hydrides are also called molecular hydrides. Now, they can be divided into three categories. The first one is called electron deficient hydride. Now, electron deficient hydrides do not have a complete octet, like say for example B2H6. In fact, all group 13 hydrides fall into this category, and that is why they act as Lewis acids. That means they are electron acceptors. So they are Lewis acids, in other words, they are electron acceptors. Then the second one is called electron precise hydrides. So electron precise hydrides, they have a complete octet, and usually you will find that all elements of group 14 will give electron precise hydrides, like say for example methane. Then the third category is electron rich hydrides. Now electron rich hydrides have excess electrons which are present as a lone pair, like say for example ammonia has a lone pair, H2O has a lone pair, HF has a lone pair, they are all having lone pair. So due to the presence of lone pair, they behave as a Lewis base. That means they are very good electron donors. And one more thing is that due to the fact that they have lone pair, so that is why they facilitate hydrogen bonding. So they facilitate hydrogen bonding due to the presence of lone pairs. Next we come to metallic hydrides, the third type of hydride, metallic hydrides. Now metallic hydrides are also called non-stoichiometric hydrides. They are also called interstitial hydrides. They are usually formed by D block or F block elements. Now in D block and F block, the groups 7, 8 and 9 elements do not form a hydride. So the elements of group 7, 8 and 9, they do not form a hydride. And group 6, only chromium is able to form a hydride. Now these hydrides, they conduct electricity and one more thing is that they have a non-stoichiometric formula, like lanthanum hydride is LaH 2.87, then ytterbium is YbH 2.55, then vanadium is VH 0.56. So you can see that why they are called non-stoichiometric hydrides, because the hydrides do not follow stoichiometry in their formula. Now, what actually happened was that when it was studied that why they are having non-stoichiometry, initially it was thought that in the metal lattice, the hydrogen occupies voids, or you could say interstices. So hydrogen occupies voids, or you could say it occupies interstices. Now, due to the fact that hydrogen is occupying the interstices, it is disturbing the stoichiometry. Now, one thing is, after detailed analysis, it was found that this particular explanation holds true for very few metals like nickel, palladium, cerium and actinium. And one more thing is that for hydrides of other metals, it was found that the lattice itself is completely different from that of the parent metal atom. So once again, this particular explanation that non-stoichiometry is present because hydrogen occupies voids or interstices, this explanation was true for only these elements, and for the rest of the elements it was found that the lattice itself is different from that of the original parent metal atom. Now the thing is, it is very clear that D block, F block elements, thanks to non-stoichiometric hydrides, they have the capability of absorbing hydrogen, and that is why they are used for catalytic reduction. In catalytic reduction, these hydrides are preferentially used. Now, some of them like palladium, platinum, can store a large amount of hydrogen. So therefore they are used for hydrogen storage. So some of these elements like palladium, platinum, etc. can store a large amount of hydrogen, and therefore they are used in hydrogen storage. Next we come to water. Now water, first we will discuss the physical properties of water. First of all, we all know that water is colorless and tasteless, and one more thing is that water is capable of hydrogen bonding. So due to that, it has a high melting point and boiling point both. So it has, and due to the same reason, it has got high latent heat of vaporization as well as fusion. Another thing is, it also has high specific heat. It has got high conductivity, thermal conductivity. High surface tension. Then high dipole moment. And high dielectric constant. So these are all the important physical properties of water. Next we come to the structure of water. Now the structure of water is a bent structure in which the bond angle is 104.5 degree and bond length is 95.7 picometer. Thanks to the very high electronegativity of oxygen, water is a highly polar molecule. Now the thing is that the structure of ice is such that each water molecule is tetrahedrally bonded to 4 other water molecules, and in fact, to give you an idea, this is how the tetrahedral structure looks. So you will notice that in the structure of ice there are large vacant spaces like these. So due to these large vacant spaces, the volume is very high, and because the volume is very high, so that is why the density of ice is less than the density of water. So this is the explanation for density of ice being less than density of water. Next we come to chemical properties of water. First is the amphoteric nature. Water can act both as an acid and as a base, and in fact water is also capable of autoprotolysis. That means it can have a conjugate acid-base reaction with itself. Second thing is that water can give many redox reactions. During photosynthesis, water is oxidized to O2, and fluorine is capable of oxidizing water to O2. Water can take part in many hydrolysis reactions. Water can take part in many hydrolysis reactions such as these. Water can act like a ligand and take part in coordination compounds like this one. Or this one. In fact, this is actually copper sulfate dot 5H2O, and you can also have interstitial water, like water is present in the voids, like BaCl2.2H2O. So this brings us to an end of chemical properties of water, and it also ends the first part of this chapter, that is hydrogen.